this vector V1 was already present in the other vectors. So at all ends, if I have already the other vectors, I don't need considering V1. When thinking in linear system, this will mean that if we have a large system of equation, this linear independence linear independence means saying that no equation is redundant. We cannot eliminate any of the equation. Actually, we will see a way in which reduce basically the number of equations in a linear system, somehow eliminating all redundant ones. So it's linearly dependent. The opposite of linearly independent is linearly dependent. So some observations, some claims. Obviously, if a family of vectors contains the zero vector, the origin, then the family is linearly dependent. Obviously, because you can assign to zero any scalar different from zero. And you have lambda times 0 plus 0 times the other ones equals 0. If two vectors are linearly dependent, then they are called collinear. Some sense. One can be written as the multiplication of a scalar for the other vector. They're also called parallel. And I'm sorry, I have forgot registering.
Recording in progress.
So I'm gonna start now registering. Then there is an important family of vectors which is called natural basis, natural orthogonal basis of Rn, that is this one. Here it's written formally in a probably obscure way. And let me write it here. So let's start, let's say, A1 is equal, usually is denoted by E. E1 is as 1 in the first coordinate and 0 in all other coordinates. In general, Ej is equal to 0 for all coordinates different from J, and at place J, you have 1, 0, 0, and 0. The chord and the notation, the formal notation is this. The coordinate J of vector EI is 1 when I is equal to j and 0 otherwise. So A1, A2, En are linearly independent. Why? Because the sum of lambda I equal 1 to n is equal to the vector lambda 1, lambda 2, lambda n. And this number, this vector is equal to 0 if and only if all coordinates are 0. Also, and what do we have? The family I equal 1 to n is orthogonal because the scalar product between EI and EJ is equal to what? Is 0 if I is different from J, and 1 if I equal J. So two distance. Another important characteristic, a vector take x equal x1, x2, xn in Rn can be written as x equal x1, 1, 0, 0, 0, plus x2, 0, 1, 0, 0, plus xj, 0, 0, 0, 1, 0, plus xn, 0, 0, 1, equal x1 e1 plus x2 e2 plus xj ej plus xn en. So given this family of vectors, I can, represent any vector in Rn as a linear combination of those vectors. They are preliminary, they're boring, but you need some notation and some basic concept. Oh, now the definition of a linear subspace. A linear subspace is nothing more than a subset of Rn closed under linear combination. So if we take two vectors of this set, it must be the case that any linear combination of those two vectors must belong to the same space. It is equivalent to say that, but it's less economical to describe that a linear subset is closed under some and